So we all use the phrase muscle memory, right? Like you hop on a bike after 10 years or swing a tennis racket and it feels like your body's it's running on autopilot.
Yeah, it's a useful shorthand. But looking at the neurophysiology sources we have today, that phrase is, well, it's actually physically impossible.
Right, because muscles are just wet machinery, biological pulleys. They don't actually have neurons to store memories of a backhand.
Exactly, they don't have brains.
Which means the heavy lifting is entirely mental. And that is our mission for this deep dive. We are unpacking the research that shifts the focus completely from the limbs to the brain. It turns out that muscle memory is actually a highly sophisticated simulation.
It is. It's an incredible hierarchy of abstract coding and predictive modeling. Yeah. And to really understand that simulation, you have to look at the hierarchy itself.
Right.
Back in 1924, Charles Sherrington, a neurophysiologist, he framed this perfectly. He called muscle the sole executant of mankind.
The sole executant. So if the muscle is just the executant, the factory worker, the brain is the CEO. Specifically, the primary motor cortex, or M1.
Yes, M1 and the premotor cortex. And the literature shows that M1 isn't down there micromanaging individual muscle fibers. It's drafting a blueprint based on the goal.
The goal itself.
Right. The brain cares about the objective. Say, grasp the coffee cup, not the specific contraction of, bicep fiber number 402.
And we see the definitive proof of this in something called motor equivalence. Think about your signature. You can sign a check with your dominant hand, your non-dominant hand, or you really wanted to prove a point with a pen held in your teeth.
And while the teeth version might look pretty shaky, the actual style remains identical. The loops, the slants, they're the same.
Because the shape of the movement is stored as abstract code.
Completely independent of the hardware used to execute it, the plan exists as software.
But the really fascinating part of these studies isn't just the software, it's how that plan sits in the chamber before we even move. It's not constructed on the fly.
No, it's pre-compiled. This is where the startling acoustic stimulus experiments, the SAS studies, totally change our understanding of reaction time.
These are the air horn studies, right?
Basically, yes. Researchers found that if you startle someone with a loud noise right as they're preparing to move, they execute their intended movement significantly faster than their normal voluntary reaction time would allow.
It's like hot wiring a car that's already idling.
Exactly. The startle bypasses the usual voluntary go signal and just dumps the preloaded program directly into the spinal cord.
Demonstrating that the brain creates a full motor program, the force, direction, speed, and holds it there in a state of readiness.
And it isn't just holding one plan either. The research on elite athletes shows the brain is computing contingency plans in parallel.
Like a tennis player swinging, but the ball clips the net.
Right. The brain can switch to a backup motor plan in about 60 to 75 milliseconds.
Which is way too fast to compute a new move from scratch. It implies the brain already calculated the what if it hits the net scenario before the swing even started. We aren't reacting, we're just unlocking plan B.
But this high-speed execution runs into a major biological wall, which is lag. Neural signals are fast, but they are not instant.
By the time your eyes see the ball, process the image, and send the signal to the hand, the ball has already moved.
Yes. If we relied entirely on sensory feedback to know where our arm was, we would just be flailing around.
And this is why the cerebellum is so critical. It solves the lag problem using internal models.
It acts as a forward simulator. When M1 sends the command down to the muscle to move, it sends a carbon copy to the cerebellum.
And the cerebellum uses that copy to run a predictive simulation of the body's physics. It predicts where the arm should be before the sensory nerves actually report back.
Bridging the gap between the command and reality, it allows you to operate smoothly in real time, despite the biological delay of your nervous system.
It completely reframes human performance. What feels to you like muscle memory is actually the brain simulating reality, predicting physics, and managing parallel futures all at once.
It creates a seamless experience out of a chaotic reality, but it does leave us with a rather profound philosophical question about that experience.
Oh, what's that?
If your brain relies on these internal models to predict movement before sensory feedback actually arrives, are you ever actually experiencing the present moment? Or are you just living in your brain's prediction of it?
That is a fascinating and slightly terrifying thought to leave you with. Thanks for joining us on this deep dive.
Until next time.